Hi guys, you're welcome to God Academy, and in this lesson I'm going to take you through representation of a phasor as a complex number. In our previous lesson we went through power in an AC circuit, or sorry, alternating circuit, and we saw the different types of power. So here we are trying to employ the use of complex numbers to simplify alternating circuits. So generally, for every complex number, we have an operator I. That is from algebra, right? But because current is represented as I, we don't want it to, conflict. So we use the operator J whenever we are trying to use complex number in. So the operator J, take note, operator J. So mathematically, Z is equal to X plus IY is supposed to be the general notation for a complex number, where X is the real part and Y is the imaginary part. Similarly, when I take a phasor, right, as you did in the Phasors, a phasor here, and I represent this as X, this as Y, any, right? And this is simply what? My Y. Or no, let's say my current I. Okay. So here, and I make here theta. So this is a phase difference. This one can be modeled as a complex representation of a complex number in an Eigen diagram, right? Remember, in an Eigen diagram, we have the real part, which is X. We have the imaginary part for the Y, right? Then the complex number is any point within the space, and the modulus is just the magnitude. Then the argument is the angle this complex number is making with the positive real axis. So for us to employ complex numbers in alternating current, we just want to assign the parameters we have. So here we are dealing with impedances, okay? You will try to assign the various impedance to the respective components of a complex number and use that same thing to also simplify power in an AC. Okay. So remember that in an in a resistive circuit, or a purely resistive circuit where you have a resistor, the voltage and the current are in phase, right? They're in the same phase. So everything, there is nothing like a phase difference. In a purely inductive circuit, remember that you have your voltage leading the current I by 90 degrees. And in a purely capacitive circuit, we have the current rather leading the voltage by what? 90 degrees as well. Now, because of that, we can assign a resistor be the real part of the complex number, real part. So we can, assign real part to a resistor. Then now, for the imaginary parts will go for the reactances. So we can have a positive imaginary part, then we can have a negative imaginary part. So a positive imaginary part will go for an inductive circuit, because in an inductive circuit, the voltage is leading. That is why I want to make a positive, right? So in an inductive circuit, the voltage is leading. So you're going to have any positive imaginary number representing our inductive component. Then a negative imaginary number will represent the capacitive component. So here, if we are looking at impedance representation, the pure the raw part, the raw part will be represented as a resistor or resistance. Then our capacitive reactance will be represented as negative imaginary parts, and positive imaginary parts representing the inductive reactance. So let's see an example here, right here. So this express in rectangular and polar notations. A resistance of 20 ohm. B a resistance of 20 ohm in series with an inductance of 0.1 henries. Then the C is a resistance of 50 ohms in series with a capacitance of 40 microfarad. So we've been given some impedances here, and we are supposed to represent both in rectangular and polar notation using complex numbers. So for the first one, A, you see that A is a purely resistive circuit. So a purely resistive circuit represents a purely raw complex number. It only has a raw part, no imaginary part. So you simply say that 20 plus 0j or j0, right? 20 plus 0j. And now this is for the rectangular section. For the polar notation, since it is a purely resistive, remember that on the argon diagram, if you have a number falling on the row axis, it doesn't have any argument. The argument becomes zero, right? Because it is very parallel to the positive real axis. So here our angle, which is the argument, becomes 0 degrees. As simple as that. Let's check for the B. We have a resistance of 20 degrees, 20 ohms, and it's in series with an inductance of 0.1 Henry. So in impedance representation, don't be tempted to write the inductance. You have to find the inductive reactance. So what is the inductive reactance? XL. XL is 2 pi FL, right? So this gives us 2 times what pi. My frequency is given as 50 ohms. 50 hertz times my L 0.1 Henrys. So this gives me 110 31.42 ohms, right? Therefore, I can say that since that one is for inductor, it's positive imaginary part. So 20 plus 31.42 J. Okay, and that's for the rectangular component. We can represent this as a polar component simply by finding our magnitude and go our argument. To find the magnitude, you simply take the square root of the squares of the respective impedances, right? You're going to have square 20 squared plus 31.42 squared. That gives 37 points. So I have 37.25 ohms. So this is the magnitude. So having written the magnitude, we need the angle. So the angle too, we are using tan. Okay, so this is the same as the complex notation. So we are using tan. So tan inverse. So tan inverse of 31.42 over 20. Remember, it's always the imaginary over what the real part, right? The imaginary over the real part. So that gives tan inverse, you punch tan inverse of the expression 31.42 over 20. That is 57.52 degrees. So angle 57.52. So that is the B. Now finally the C. Here we are having a resistance of 50 ohms in series with a capacitance of 40 microfarad. So 50 ohms becomes a real part plus. Now we need our capacitive reactance. So XC is always equal to 1 over omega C, which is minus 1 over omega, which is 2 pi FC. As simple as that. So our frequency being 50, we're going to have 1 over 100 times C, which is 42, no, 40 times 10 to the power negative 6. So we can simply say 10 to the power 6 over, we have 100 pi, right? So over 100 pi. So what do we get? Over 10 to the power 6. Okay, so when you find your capacitive reactance, you're supposed to get 79.6, 79, So 79.6 J. Please, the sign becomes negative because we are dealing with capacitance, not positive. Becomes negative. I introduce my negative, right? Then if I were to convert this one to the polar form, likewise as we've been doing, we take square root of 50 squared plus 79.6 squared, and that gives 94. So my magnitude is simply 94, right? 94. Angle, what's my angle? So if you have tan inverse of 79.6 over 50, and the 79.6 is negative 2, so negative, that's negative 57.87. So it is lagging. Negative 57 point. So this is how we represent the respective or the various impedances using the complex numbers. So finally, let's end everything with calculating power using the complex notation, right? So calculating power using the complex notation. So in our lesson on power in AC, you realize that we identified three main categories of power. We have the first, which is the absolute or the total power, called the apparent power. It's represented as S. Okay, so the S is the total power, and I said that the total power is always equal to the total current times the total voltage. When you want to apply the complex number approach, to find the total power S is given as your V times the conjugate of I. So VI star, where star here is representing the conjugate of I. Okay, so that is the technique. So the results here in complex domain give us P plus JQ, where P now represents the active power and the Q represents the reactive power, as simple as that. So just calculating your power in the complex domain, you end up getting your active and your reactive at the same time. So these are some few formulas you're supposed to know, right? Let's see a very nice example here. So the potential difference across and the current in a circuit are represented by 100 plus J200 volts and 10 plus J5. Okay, sorry. So so the potential difference across and the current in a circuit are represented by 100 plus 200 J volts and 10 plus J5 amps, right? Calculate the power and reactive volt amps. Calculate the power and reactive volt amperes. So we need to find the power and the reactive volt amps, right? So here we've been given the potential difference and we have the total current. So how quickly can we find the power, and we want to employ complex numbers here? So remember the general formula, S is equal to VI hash. So S is equal to, what's my V? My V was given as 100 plus 200J, right? So have 100 plus J200 multiplying 10 plus, since it's the conjugate of a complex number, you only have to negate the imaginary part. So minus 2, no, minus 5j, right? Minus 5j. Then you do this simple multiplication. So when you simplify, you can point this directly on the calculator. You set it to complex mode 2, then you enter 100 in one bracket plus 200i multiplying another bracket. We have 10 minus 5i, and it gives 2000 plus 1500i. 2000 plus 1500. So this is it. So as you know, 2000 represents our active power. So our power 1000, and 1500 is our reactive volt amperes. As simple. So this is all I have for you in this lesson, and see you in the subsequent ones as we look at three-phase and the others. Don't forget to subscribe and also share as well.